The sunlight at Saturn is 1% as bright as it is here at Earth. And if you do photography, you'll appreciate, oh, it's going to make it harder to take pictures out there at Saturn. But they have been taking thousands of pictures since 2004.
Since I'm a radio man, I'm kind of fascinated with the radio system of the Pioneer and the DSN. And I'm very impressed by the fact that all of these data are received from a distance of just about exactly 1 billion miles. At this distance, if you are transmitting 1,024 bits per second, at any given time there are 5.5 million of those bits strung between here and Saturn, traveling at the speed of light, 5.5 million. And they're spaced 182 miles apart. With that, I'll quit.
How long does it take for an image to get from Cassini to Earth, like to get the data here? And my iPhone, I think, has 8 megapixels. What's Cassini have?
1 megapixel.
One. Huh?
And it's black and white.
We know how to convert that into a brightness. It tells us how much light is coming from that pixel. And that's calibration. And so we know that, and then we do that in several filters to make a color picture. If you're making a natural color, we choose blue, green, and red. We composite them together. We know pretty much how the balance goes between those three, although we don't really know it to a really high degree of accuracy. So there's always some, mushiness about just exactly what true color is. I could never promise you that something was exactly true color. But that's how you do it, just to make a pretty picture.
Titan was, in some sense, a disappointment with the Voyager missions because the absorbing and scattering processes of the Titan atmosphere were exactly mismatched to the capabilities of the Voyager camera. Where the Voyager cameras were cutting out in sensitivity as you go to longer wavelength, that's where it turns out you could stand a chance of seeing down to the surface of Titan in the near infrared if you knew what spectral regions to look at, what spectral windows to look in. So between the end of Voyager and getting Cassini rolling, people copped on to this, that there were spectral windows you could actually see down to the surface of Titan, and we equipped our cameras with those filters.
We colorize our images with filters, and it takes anywhere from an hour to 90 minutes for the image to get from Cassini here to the Earth.
The whole megapixel image to...
Well, the megapixel, let's see. We do 140 kilobits per second. Okay. So it takes 10 seconds or so, roughly, let's say 20 counting overhead, to get an image down here once it starts. But Saturn is an hour-and-a-half light time away. So when Cassini starts to send a signal, her bits don't get to the ground for an hour and a half.
For an hour and a half.
Yeah.
Gotcha.
And so when we want to signal, send something to Cassini and have it answer, we have to wait anywhere from 2 to 3 hours. Yeah.
Wow.
It just means Cassini has to be very smart. She has to basically have commands on board to keep her going, typically for 10 weeks at a time. Where to point, where to look, when to send data back. And so very, very smart spacecraft.
The type of image processing? It depends for what purpose. I mean, if you're talking about just making beautiful images, we have to work with calibrated images, so we know how to calibrate. We spent a lot of effort to learn how the instrument responds and how we take the number that comes out of the camera, so to speak. We just call it a data number. It could be 4.
The pictures were converted to an electronic number code, and the numbers were transmitted to Earth via radio waves. Computers then use the numbers to reconstruct the images.
The suite of instruments being carried that are on the Cassini spacecraft is the most sophisticated suite of instruments ever taken certainly to the outer solar system. It's remarkable. I mean, we started with Voyager. I think there was one computer for operating all, whatever it was, 8 instruments. But we have 12 scientific investigations on the orbiter alone. And each of them has sub-investigations, like the imaging investigation has 2 cameras. Each of them has their own microprocessor, and it's so many more capabilities built into the Cassini spacecraft that makes our job, a lot easier.
What's the data rate back to Earth, and do you have to buffer the images on the spacecraft?
Oh yeah, we have to buffer, and I don't remember the data rate. Isn't that ridiculous? But I don't remember. I don't even want to say because I'll guess and I'll get it wrong, and this is being filmed and it'll go out there and I'll forever be wrong, so I won't say it.
I did have a question about the temperature. It's so damn cold out there, and I'm wondering, for 14 years, Cassini's been performing and doing things fairly actively. I'm wondering, is the cold a hindrance or a huge challenge, or is it actually like a preservative that keeps things in order when they're...
The thermal part of spacecraft design is, as far as I could tell, I'm not a spacecraft engineer, but I've been around them for a long time. That's the most challenging part. Thermal gradients just screw everything up. So you want to reduce thermal gradients. I don't think it's so much the temperature, but it's gradients.
Oh, wow. It's cold at Saturn, let me just tell you that. So Saturn's a very cold place, and one of the things that's involved on the spacecraft team is we have all these subsystems, right? So there's a thermal subsystem that actually studies all of these temperatures, and they have heaters, they have all these blankets that are on the spacecraft that's really to protect our instruments, because everything there is frozen. So water there would be frozen, so it's cold.
I don't really get my jollies, building or thinking about instruments, but I have to say we had just a really lovely collaborative effort in building the cameras, and it shows. They work phenomenally well.
Across from the front to the back of the camera was a terrible thing because then it screws up. It's a long focal length camera. I mean, it's folded, but still, you get distortion because of that thermal gradient. So we have heaters in the cameras that reduce the gradient or try to keep it stable.
Well, okay, like the cameras. Let me describe the Cassini cameras. They're the most sophisticated cameras. In fact, Cassini's payload is the most sophisticated payload that was ever taken into the outer solar system. In our cameras, we have 2 of them. We call them cameras. They're actually telescopes, and outfitted with many spectral filters. That's why Cuneo can look at the hexagon and all sorts of different spectral filters, and they kind of slice the Saturn atmosphere and give us a shot at different levels in the atmosphere. Other images, like the one our mosaic is made of, this particular mosaic, whereas our red, green, and blue, we can use those to make what you might call natural color, but they also have scientific purposes.
Our cameras have 2 filter wheels. Essentially, you can take a green, blue, and magenta filter, not magenta, blue, green, well, whatever the 3 colors you pick, and colorize them, right? It has infrared filters that penetrate the haze. And so each of these filter wheels, you actually rotate that filter into the image path and take an image, then rotate another filter, take another image, and they're combined and colorized on the ground.
So the colors you end up with represent what you're actually looking at, or is it?
They can, or they can represent some of the false colors that you've seen, like the red hurricanes and things like that, that accentuate levels of elevation or of chemical constituents. Okay. A lot of the pictures you've seen were natural, but some of the others were false colored to highlight whatever meteorological or chemical item you're trying to look at.
But you can get true color. You take those filters and add them together in different ways, and you get the true color that you would see with your eyes in those pictures.
This is produced in false color because it gives us a little more contrast to the features that we're looking at. The colors that go into this are ultraviolet, violet, and green.
And then there's many other capabilities in the cameras I don't have the time to go into, but I will tell you, first you need to know, if you ask this question of any planetary scientist, you'd get a different answer probably from each one. So we're not so much in the business of identifying whether or not it's, well, I can't even guess right now, but we're not identifying particular chemicals or chemical bonds. what we can do is we can say that we have an ice on the surface that absorbs a lot in the infrared, but maybe not so much in the ultraviolet. In some sense, colors is really the spectral information that we can get with the cameras.
Rather than have a picture that's got, let's say, you know, Enceladus looking blue, green, red, we deliberately, you know, composite them. So we cheat a little bit, and we, you know, take the 3 images, put them on top of one another, and put it in the final image. But that's for just public release. I mean, there's lots of things we do to extract scientific information. I could bore you with it for hours. I mean, you know, so.